Let's explore C++ multimaps. These are key-value containers that allow duplicate keys, which is made possible through the standard : multimap construct in C++. So, what exactly is a multimap? Firstly, it is an associative container. This means it stores data in key-value pairs, similar to a dictionary. The most important feature of a multimap is that it allows multiple elements with the same key. In a regular map, keys must be unique, but in a multimap, keys can be repeated. Elements in a multimap are automatically sorted by their keys, using a comparison function. The default comparison is in ascending order. Multimaps are implemented as balanced binary trees, typically a red-black tree, which ensures efficient operations. Finally, multimaps are part of the C++ standard template library, often referred to as the STL, providing a ready-to-use and optimized container. Now let's see how to create a multimap in C++. To start, you need to include the map header using the statement #include_map. Inside your main function or any other relevant scope, you can declare a multimap. The basic syntax is standard : multimap, followed by the data type of the key and the data type of the value, enclosed in angle brackets. For example, standard : multimap, standard : string, int scores, creates a multimap where the keys are strings and the values are integers. To define a custom comparator, you can specify it as a third template parameter. For example, standard : multimap, standard : string, int, standard : greater, standard : string, reverse scores, creates a multimap that sorts keys in descending order. You can initialize a multimap with elements using a braced list of key-value pairs like this: standard : multimap, standard : string, int, student scores equals Alice, 95, Bob, 89, Alice, 92. Notice that the key Alice appears twice, which is perfectly valid in a multimap. Let's explore some basic operations you can perform on a C++ multimap. Consider that we have a standard : multimap called grades, which stores string keys and integer values. To insert elements into the multimap, you can use the insert function. For example, grades.insert make pair Alice 95 and grades.insert Bob 87. You can also insert elements with duplicate keys such as grades, insert Alice, 92. To determine the number of elements in the multimap, use the size function. For example, size_t_size equals grades.size will return 3. To check if the multimap is empty, use the empty function. For example, bool is empty equals grades.empty will return false. To find an element with a specific key, use the find function. For example, iterate equals grades.findAlice. This will return an iterator to the first element with the key Alice. If the key is not found, the iterator will point to grades.end. To count the number of elements with a particular key, use the count function. For example, size_t_count equals grades.countAlice will return 2, because there are 2 entries with the key Alice. Now let's delve into how to effectively work with duplicate keys in C++ multimaps. Suppose we have a multimap called student scores containing names and scores, where some students have multiple scores. To access all the values associated with a specific key, you can use the =range method. This method returns a pair of iterators. The first iterator points to the beginning of the range of elements with the specified key, and the second iterator points to the end of that range. For example, auto_range equals student scores =range Alice. You can then iterate through this range using a for loop to access each key-value pair. In this loop, auto_it equals range.first, it not equals range.second, ++ it allows you to traverse each Alice entry. Remember that elements with the same key are stored in the order they were inserted. In addition to =range, you can use lower_bound to get an iterator to the first element with a given key, and upper underscore bound to get an iterator to the element just past the last element with that key. When working with multimaps, keep in mind that a single key can be associated with multiple values. The equal underscore range method is specifically designed to handle this scenario efficiently. Now let's explore different ways to iterate through a multimap in C++. Consider a standard : multimap called scores, which stores string keys and integer values. One common method is using a range base for loop. In this approach, you can iterate over each key value pair in the multimap using the syntax for auto and pair : scores. Inside the loop, you can access the key using pair.first and the value using pair.second. Another way to iterate through a multimap is by using iterators. You initialize an iterator to the beginning of the multimap, and then loop through the elements until you reach the end. Inside the loop, you can access the key using @first and the value using @second. Elements in a multimap are always sorted by key, and elements with the same key appear in the order they were inserted. Iterators in a multimap point to standard : pair constant key, T objects, where T is the value type. It's important to note that iterators remain valid after insertions, which is different from vectors. If you don't need to modify the elements, you can use gbegin and send to obtain constant iterators. Now let's see how to remove elements from a C++ multimap. Suppose you have a standard : multimap called scores. One way to erase elements is by specifying the key. The erase function with a key as its argument removes all elements with that key. For example, scores.erase Alice will remove all entries where the key is Alice. This method returns the number of elements removed. Another way to erase elements is by using an iterator. First, you find the element you want to remove using the find function, and then you pass the iterator to that element to the erase function. For example, you find the Bob key by creating iterator called it using the find function. Then, pass that iterator to the erase function. If you want to remove all elements from the multimap, you can use the erase function with a range specified by two iterators, in this case scores.begin and scores.end. After erasing elements, any iterators pointing to those elements become invalid. However, other iterators remain valid. Keep in mind that when you erase by key, all elements with that key are removed. If you only want to remove one instance of a key, use the iterator-based erase method. Let's look at a practical example of using multimaps, a course registration system. In this scenario, you have students who can register for multiple courses. A multimap is perfect for storing this data because each student, identified by their student ID, can be associated with multiple courses. You can declare a standard : multimap, where the key is the student ID, which is an integer, and the value is the course name, a string. To register students for courses, you can insert entries into the multimap where student ID 1001 registers for C++ programming and data structures. Now, if you want to retrieve all the courses for a specific student like student 1001, you can use the =range function. Then you can iterate over this range to print out all the courses that student is registered for. Multimaps are useful here because each student can register for multiple courses. They automatically sort courses by student ID, making it easy to retrieve all courses for a specific student. Multimaps also provide efficient insertion and lookup operations. Other real-world use cases include a dictionary with multiple definitions per word, an event logging system, a phone directory, and an index in a database. Let's discuss the performance characteristics and best practices for using C++ multimaps. Inserting an element into a multimap has a time complexity of O log n, where n is the number of elements in the multimap. Erasing an element by key has a time complexity of O log n plus k, where k is the number of elements with that key. Erasing by iterator has a time complexity of O log n. Finding an element has a time complexity of O log n. Counting the number of elements with a key has a time complexity of O log n plus k, where k is the number of elements with that key. The equal underscore range operation has a time complexity of O log n. Here are some best practices to keep in mind when using multimaps. Use equal underscore range to efficiently access all elements with a specific key. Consider using in-place instead of insert for in-place construction. Use count to check if a key exists before performing operations. Be careful with erase key, as it removes all elements with that key. Use custom comparators for special sorting requirements. Consider alternatives like standard : map with standard : vector values if you need random access to values. Use const underscore iterator when you don't need to modify elements. And remember that iterators remain valid after insertions, unlike vectors. For very large datasets with many duplicate keys, consider using unordered underscore multimap for O1 average case lookups, but be aware that elements will not be sorted. If you like this video, hit that like button and don't forget to subscribe. Visit codelucky.com for more such useful content.